So you already did this the other day when you watched those Khan Academy videos, and that's a pretty good introduction to exponential growth and how exponential growth works. But it is definitely not the entire story. So we're going to go we're not going to go back over anything that you've already done when you watched the Khan Academy videos and took notes, but we are going to go over we're going to basically take the ideas that you watched and took notes about in the Khan Academy videos and expound upon them. The first one that we're going to use is exponential growth models. Okay. And so that's the first one that we're going to go through. And so I'm going to come back here and check these off as we do. And so here's why exponential growth is something that is so powerful and is something that people in science and math have studied for a long time. Obviously, you guys got the idea that y equals 2 to the x is some type of function that grows really, really quickly. I think the one in your notes that you used specifically was y equals 3 to the x. And so, hang on just a second. I messed with my viewer. There we go. That's what I want. So these things grow really fast, really quickly. And to give you an idea of why this stuff is so important and how fast it grows, I'm actually going to use, and I know some of you aren't going to necessarily be thrilled with this, but I'm going to use COVID-19 to explain this. Okay, so let's talk about the flu. Okay, we've talked about in class what this R naught number means. And that's when someone is sick with something, how many people they give that disease or infection to. So for the flu, we've had lots of years of studying the flu. R naught is roughly about 1.3. Okay, so for every one person that gets it, they spread it to about 1.3 people. And and here's what that actually practically means. The incubation period for the flu, I looked it up yesterday, is approximately 1 to 4 days. Okay, so here's what that means. For the first 1 to 4 days that I have the flu, that's when I can spread it to other people. Okay, and on average, I'm giving the flu to 1.3 other people. So let's draw a picture of what that actually looks like. Okay, so if this is me right here, smiling face, and I've got the flu, then I might give the flu to just one other person. So let me actually come back here and make another one. Nope, I don't want to change the size. There we go. And I might give it to one other person. Okay. And then this person, let's say that this person is, let's say that this person's name is Aiden, and I give the flu to Aiden. She might give it to 2 people. Okay. All right. And then, oh, now it won't let me. Uh-oh, I messed up. Okay. And so the growth curve, and then it keeps going. Okay. So this person might give it to one person, and this person might give it to one person, so on and so forth. Okay. But you can see how it grows. It kind of grows almost linearly. The growth curve for something like the flu would look something like this, where a small number of people would have it, and then it would increase, and then there would be a peak, and then it would come back down. It would look something like that. But let's talk about specifically exponential growth with something like COVID-19 and exactly why this is so dangerous. Okay. We don't know yet, but our best guess is that the R naught for COVID-19 is between 2 and 3.1. Okay. So if one person gets COVID-19, they're on average for 14 days. That's the incubation period of COVID-19. Again, this is our best guess as of right now. They're on average giving it to 2 other people. So what would that look like? Well, here is patient 0. Okay. And if they have COVID-19 and then they give it to 2 people, then what happens to these 2 people? Well, then guess what? They give it to 2 people. Okay, so this person gives it to those 2 people, and this person gives it to those 2 people. And so we have this little tree that's forming here, and it kind of looks like a family tree. Okay, and then these 4 people are all giving it to 2 people. Okay. Okay, so it won't let me, oh, it will let me zoom out. And now we can't see my picture. But you can see how fast it's growing. And we can actually measure this. Yes. We can actually measure how fast this is growing. And I'm gonna do this one more time. I know I'm messing with my earlier stuff. Okay, so so let's talk about how we can measure this. Okay, so this first person got it, and that equates to 2 to the 0th power. Okay, so 2 to the 0th power is 1. So on the first person that got it, 1 person has it. Well, then they share it each to 2 people. So all of a sudden, now 2 people have it. And then when they share it with people, now sorry, I was jumping ahead of myself. 4 people have it. And then when they spread it to 2 people, then 8 people have it. And then when they spread it to 2 people each, then 16 people have it. And you can see this rate of growth. Now, the incubation period for COVID-19 is about 2 weeks. It's 14 days. So this takes weeks to happen, but it can grow really, really fast, really, really without us really being aware that it's growing really, really fast. Because at first we're seeing low numbers of cases, and then all of a sudden it shoots up. It zooms up towards very high numbers. Think about this. By the time this group of people spreads it, they're spreading it to 32 people, then 64, then 128, 256, 512, 1,024. So if COVID-19 was spread in one day, then in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 days, 1,024 people have it. Okay, now that's not the way it works. It doesn't spread, this doesn't double every day, but it doubles every 2 weeks. Okay, so then by the time that maybe we don't even realize, all of a sudden, if I zoom out to like the 10th week, 2 to the 10th, two times 2 times 2 times 2, 10 times. Okay, that's where we are, 1,024, 2048, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so in a span of 20 supposed weeks, about 20 weeks, over 1 million people have this disease, whatever it is, COVID-19. Okay, so if I come back here, that growth curve would look like this. It would start small and it would spread, and then all of a sudden it would be zooming off to these very, very high numbers. Okay. And that's why something like this is so dangerous, because on average, 2 people are getting it from every 1 person that has it. And it starts off slow and then it zooms off towards millions and millions of people. I mean, we could keep going. If this is 20 weeks, then 21 weeks, 2 million, 23, or 22, 23, 24, 25. And all of a sudden, we're in these astronomical numbers of people that have this disease. Okay. So here's the cool thing, and this is the last thing we'll do before we get into some more gritty math. Jesus actually understood exponential growth, which is a really cool thing. I'm certain that when Jesus was on the earth, he knew of exponential growth, and here's why. We talked about this, but if I have one person up here who's on stage speaking, and he is speaking every Sunday, and every Sunday he brings 1,000 more people to his church, that's pretty good, right? I mean, in 1 year, he would have 52,000 people in 1 year. But if I use a discipleship model, which is the model that Jesus used because he understood exponential growth, what did Jesus do? He didn't say, I'm going to go speak and bring 1,000 people to follow me every single week. He said, you know what? I'm going to take 3 years and I'm going to really invest myself into 12 people, but even more specifically, 3 people, right? This is the idea of being a 100x leader right here. Jesus was 100% healthy, and then he multiplied himself into the lives of 3 other people, right? Peter, James, and John. And then what he did, when he was done with that, is he said, okay, now that you all are like me, I've been 100% healthy, I've invested in you 3, I've multiplied myself into you. What did he ask them to do? He said, now I want you to turn around and I want you to do the same thing. So what did they do? They turn around and each of them picked 3 people that they invested into. And this is how Jesus grew the church. This is gaining 52,000 people per year. This is a slower model, but this has far wider reaching opportunities for influence and impact. And this is the reason why Christianity as a movement, as a religious movement, still exists today, because Jesus chose to use an exponential growth model instead of what we would call a linear growth model, which is like this, 52,000 people every year. Okay. We're not going to sit here because we don't have the time to do this math, but it's not long before an exponential growth model like this overtakes this model, which is a linear growth model. Okay. That it would take a few years, but it's about by year 10 when this model is growing so much faster than this model. Okay. So pretty cool thing that, yes, we're seeing the ideas of exponential growth today with COVID-19, but also pretty cool to go back and think about how Jesus saw leadership. And this is what we would call a discipleship model. And that's the model that Jesus used to change the world. He didn't say, I'm going to try and go speak to tons of people and get them to follow me. He said, I'm going to invest everything that I have. I'm going to invest all my time, all my energy into 3. And then I'm going to turn around and ask them to do the same. Okay, so pretty cool. All right, so there's just a little bit on exponential growth models. Let's get into the nitty gritty math, how this works. So obviously, if you want to have your book out, you can. That will help you. You can follow along, but you don't have to. But the exponential function looks like this. F of x is some number a to the x. A must be greater than 1. The domain of this function is -infinity to infinity. The range is 0 to infinity. It does not go below a y value of 0. If we were to graph it, it looks like this. It would cross here at 0, 1. And I'll graph it in orange. It would start here and then it's zooming off like this. Okay, so this is f of x equals a to the x. okay? It has an intercept, like we just said, at 0, 1. And it is continuous. The only thing that is different about a to the negative x, raising an exponential model, all the characteristics of this function are the same, but it decreases. So it goes in the other direction, like this. And this point right here is 0, 1. Okay. I'm just double checking on the technology here. Has anybody tried to raise their hand and I haven't seen it? Nothing has popped up. So shout out if you've raised your hand and asked a question and I have not seen it.
I tried to ask a question. So what if a is less than 1? Would that be like an decay graph?
So if I raise Alec, like, let's see here, 1/2 to the first power, or to the x, what would happen there?
It would just be a smaller fraction.
Right.
No,
so what's happening is it's getting smaller and it's approaching 0, right?
Well, can x be negative?
Yeah, I mean that's what we just went over right here, right?
Oh, okay. Sorry, my bad.
Yep. So which would be exactly what you described right here, something with a is less than 1. So instead of a being less than 1, we're talking about it in terms of x being a negative exponent. Good question.
Okay, thank you.
Yep. So you guys probably figured out from your homework that transformations of these functions work. So for example, if I have f of x equals, and you had to do this in your practice problems that were due on Monday, like x plus 1, this would be a shift 1 unit to the left. Okay, and f of x being a to the x minus 1 is a shift to the right. So all our normal transformations work. F of x being a to the x plus or minus 1 would be a vertical shift, and that's all we're going to say about that. So just wanted to make you aware that our shifts that work for other functions work for this one as well. Okay. For many applications, there is an irrational number that we use the base of, and you've seen this number before, and it's the number e. I'm going to start a new page down here. E is approximated to the 2.718281828, and then so on and so forth. It's a never-ending, never-repeating decimal. It's an irrational number, okay? And this is approximated from this function, and you don't necessarily need to know this, but when you use this and then you plug in really large values for x, then you get e. You get this number e. So that's where this number comes from. And so e is another version of the exponential function. You'll often see something that's like y equals e to the x. And you guys need to be able to do that regularly, mainly in your calculator. So I'm going to give you some examples really quickly. If you have your calculator near you, I want you to pull it out, and I want you to try and use your calculator to approximate y equals e to the x when x is 2, or sorry, when x is negative 2, when x is 0.25, and when x is negative 0.4. Take a second and do that right now, and then I'll give you about a minute, and then I'll call on you when we're done to have our answers, just to make sure you know how to plug this in your calculator and you've had some practice doing that. Okay? So take a minute to do that. Isabel, I see you. Do you want to ask your question now?
Well, you seem busy now, so I was gonna tell you that I'd just come back.
Okay, that's totally fine. We'll talk during my office hours later.
Okay.
All right.
Goodbye.
Bye.
Can we also do this in Desmos?
You can do this in Desmos. Yep. In Desmos, you'd probably have to graph it, Alec, and then and then you would want to put, well, let's see, I'll do it here.
What was the last one?
It was to the negative 0.4.
My screen is like zoomed in and it won't zoom out.
I mean, it's zoomed in on like what, Sean?
It's on your screen, but I can like move it around and I can like look at what you're typing right now.
Yeah.
But I have to move to see the graph.
What happens if you get off the call and then come back on?
I'm gonna try that. Bye.
Okay, so let's see here. I'm gonna call on people. Let's see. Kendall, I saw you with your calculator. What did you get when X was -2?
That's the only one I have not done. I've done the other two.
Okay, well, give me either of the other two.
Okay, x equals negative 0.4 is 0.67.
Okay, negative 0.4 equals 0.67. That's right. Okay. Riley, which one? Give me one of the other ones. Riley, you're muted.
Sorry, I did
Sorry.
-2, but like it's not graphed. It's like no
What did you
solution
get for the
that.
value?
Well, I put in my calculator and it just says error.
So when you type in e raised to the power of -2.
Yeah, same here.
I just play E raised to the -2.
Oh well, I got 0.135.
There you go. That's right. 0.135. Okay, and then
So
let's see. Zoe Mitchell, give me the middle one.
how do you differ?
It's 1.284.
Yep. Very good. Okay. So that's just
I have a
practice.
question.
Yeah, what's up, Alex?
In theory, if E is raised to a number, wouldn't Y just be a straight line?
You cut in and out. Say that one more time. Okay, Alec, if you think of your question, ask it later, but I'm having a hard time hearing you, so we're going to move on. Okay, so next, what we're going to talk about is something very, very cool that you guys have all heard of before, and I know that you've heard of it because I was there when we talked about it, and that's compounding interest. Okay, and there's two ways to teach compounding interest. Okay, and there's always a couple of ways, and there's teachers do it differently all over the place. One way is to say, hey, here are the formulas for compounding interest, get used to using them, now use them. But the other way is, of course, like you guys know me by now, to try and explain, hey, where do these formulas come from? How do they work? And then at the end, show you the formulas. So we've got 14 minutes left in class. So I'm not going to take super long to do this, but I'm going to try, and it's my best to give you an overview of compounding interest, how it works. We're going to do a couple examples. I'll give you your practice problems, and we'll be done for the day. Okay. So we talked about compounding interest, and we talked about compounding interest at Booster with Chris Carneal and his CFO, Stan. For those of you that were there that day, the juniors who are in entrepreneurial economics. And we talked about it with his car. Okay. Do you guys remember this? Talked about his car payment. and how a normal, an average car payment for a car is maybe $500 for 5 years, something like that. And they talked about how Stan had been driving this car for 21 years. So that means that, 21 minus this 5 years, that means for 16 years, he was not making a car payment. And Chris made this claim that if he's investing that $500 instead of having to make this car payment, that this $500 has turned into a lot of money. Okay, that was his claim. So what we're going to do today is we're basically going to see, is his claim correct, or was he just making that up? So here's the idea. There's a couple of things, a couple of values that we use and variables that we use to think about compounding interest. And that's this idea of P. P stands for principal. That's a principal amount, an original amount of money that's put into compounding interest. In this case with Stan, our principal would be $500. If I want to find how much principal, so at time equals 0, P just equals P. That's really easy to do, right? If time equals 0, I haven't invested it, it's not earning any interest, then that amount that I'm putting in is there. When time equals whatever time, it could be a month, it could be a year, it could be a quarter, then how to find the amount of principal I would have at that time would be the original amount plus the original amount times the interest that it has earned. Okay, so if it was $500 and it earned 10% interest, 10% interest on $500 is 50. So this would be 500, our original amount, plus 50, because this would be 500 times 10%. Okay, so that comes out to be, we can factor this, and that factored becomes P is 1 plus R. And this is how this is most commonly written right there. Okay. After 2 years, it would look like this. Our principal after 2 years would be the original amount P times the first year, and then again times the second year where we've earned this interest rate again. And so that would look like P times 1 plus R squared. And hopefully you're noticing a trend here. And we can generalize this statement to be that the principal amount, the amount after a certain amount of time T, will be represented by this formula. 1 plus the interest rate raised to the power of T. Okay? But there's all this crazy stuff that we can do about figuring out, what if we want to do it in months? What if we want to do it in quarters? What if we want the interest to compound over years? How would we do that? And we're not going to go through the derivation of this, but basically how that works is the formula comes out to this. So we're going to look at two different ones. For n compoundings per year, this is the formula that we use. Okay, so n is the number of months or the number of quarters or whatever we say. We are going to divide that interest rate, whatever that interest rate R is, by n, and then also multiply this value T by n. For continuous compounding, so the difference between continuous compounding and a certain number of compoundings per year is basically when we're thinking about an investment or an interest rate that increases without bound. So it increases without bound forever. That's this famous formula that you've all heard of before that is called PERT. And again, here, P is the principal. E is literally the number E. R is the interest rate. And T is the amount of time. Okay. And so let's see if what Chris said was true. I think the exact claim that I was correct on that day that we were there was that this $500 per month has probably turned in, I think the exact amount he said was 384,000. I don't know why he said that amount or where that came from, but that was the amount he said. And so we're going to see. So I actually have looked up all of this data, and if in 2004, that would be the year that he would start taking this car payment, and instead of making a payment towards the car, he was investing it. If he had taken that principal $500 and invested it over the course of from 2004 to 2020, the value of the S&P 500, which is kind of a good measure of the stock market, grew from, let me see here. In January 1, 2004, it was $1,132.52. And January 1 of 2020, the value of the S&P was $3,278.20. And so we need to find that growth rate. And so in order to find that growth rate, what we're going to do is we need to subtract these two numbers. So I'm going to subtract $3,000, and I'll have to look up what it is. 3,278.2 minus 1,132.52, and that comes out to $2,145.68. 2145.68. Okay, so that's the actual amount that the S&P 500 grew over that time. And so what we're going to do to find the percent growth is we're going to do this. We're going to divide the increase by the original number, which was right here, and multiply the answer by 100. So we're going to do, so percent increase is going to be 2145.68. And I'm going to explain why we're doing all of this in a second. Because what we're trying to do right now is we're trying to find the interest rate. So I'm going to come back to my calculator, 2145.68, and I'm going to divide that number by our original, where we started in 2004, which is 1,132.52. Okay, times 100. Okay, and that's 189%. So what that means is that in this time from 2004 to 2020, any amount of money that I would have invested in 2004 is now 189% what it was. That's more than doubling. How many years was it between 2004 and 2016? 2004 and 2020. I was answering my own question. It was 16. So our average annual growth rate each year would be 189 divided by 16, which comes out to be 11.8%. Okay, so here's what all this means. All we've been doing this whole time is trying to find out at what rate per year would this amount of money have been growing if I had invested it into the S&P 500 in 2004. Okay, are y'all with me to this point?
Does this have anything to do with the car?
What do you mean? This is the car payment. So a car payment is usually around $500 for 5 years. So every month you're paying $500 for 5 years. And so remember what Chris was talking about was living below your means. You remember that? And so
Yeah.
he said, like Stan, this guy, he had driven this car for 21 years. And what most people do, the average lifespan of a car is 7 years. So what most people do is when they pay off their car payment, they get a new car. And then they have, guess what, another car payment. But he was using Stan as the example to say, hey, you should always live below your means, because if I take this $500, I don't have to make a $500 car payment. I can invest it. There's a lot of stuff that can happen with this money. So now we're going to do this formula right here. And we're going to do this right here. And our amount is going to be $500. That's our principal, times 1 plus our rate, R, is 11.8%. Okay, so we would go, now we have to do it as a decimal. So I shouldn't put 11.8. I'm going to put 0.118 as a decimal. Okay. We're going to say that this was compounded every year. So let's say that he reinvested his money every year. So N in this case is going to be 1. And he did it for 16 years. So when I'm raising it to the NT right here, NT would be 1 times 16. Okay, and I want you to do that in your calculators really quickly. Do this first. Do 1 plus 0.118, raise it to the 16th power, and then multiply that times 500. And then someone shout out what you get.
2,978.
0.78.
Is that what everybody got?
I got 2,978.
Very
I
good.
got the same answer.
Very good. There you go. So what does that number mean? That's what that $500 has turned into, the original $500. Okay. All right. You're going to have to do 2 problems where you're going to have to use one of these 2 formulas. I'm going to give you those problems really quickly because it's 9:20, and then we are going to go. So I want you to do numbers on page 186. I want you to do numbers 59 and 60. And that's it. And that